So here's something worth thinking about tonight. Right now, this very second, there are roughly 400,000 miles of cable sitting on the ocean floor. Not floating, sitting, resting in the silt and the mud at the bottom of the Atlantic, the Pacific, threaded through the Mediterranean, looped around the southern tip of Africa. Some of these cables are as deep as Everest is tall. And every time you send a message to someone on another continent, every time you stream a song that was recorded in London or pull up a website hosted in Tokyo, your data, your actual ones and zeros, are traveling as pulses of light through a glass fiber thinner than a human hair, buried under miles of ocean, dodging fish and shipwrecks and underwater mountain ranges. And the whole trip takes maybe 60 milliseconds. That's the internet. That's what it actually is, underneath all the apps and the interfaces and the glowing screens. It's a physical thing. It's glass and copper and silicon and electricity. And before any of that, it was an idea. A strange, improbable idea that almost didn't happen. Championed by people whose names you've probably never heard. Funded for reasons that had nothing to do with you watching videos in bed, and the story of how it came to exist, how it grew from a handful of computers in a few university labs into this thing that has basically rewired human civilization. That story is one of the most fascinating engineering tales ever told. And it starts, like a lot of the best engineering stories from the 20th century, with war. Not the internet itself, not exactly, but the conditions that made it possible, the fear that made it necessary. Let's go back to October 1957. The Cold War is in full swing. The United States and the Soviet Union are locked in this existential standoff, each side convinced the other is a few years away from gaining some decisive technological advantage. And then, on October 4th, the Soviets launch Sputnik. Now, Sputnik was tiny. It was about the size of a beach ball, maybe 23 inches across, and it didn't really do much. It orbited the Earth. It beeped. That was essentially its whole job. It transmitted a simple radio signal. This steady beep, beep, beep that amateur radio operators all over the world could pick up. But the psychological impact was enormous. Because what Sputnik proved wasn't just that the Soviets could put a satellite in orbit. It proved they had rockets powerful enough to reach space, which meant they had rockets powerful enough to reach the United States. The same booster that lofted that little aluminum sphere could, in theory, carry a nuclear warhead across the ocean in about 30 minutes. The American response was immediate and, in hindsight, incredibly consequential. In January 1958, President Eisenhower signed the order creating ARPA, the Advanced Research Projects Agency. Later, it would get a D added to the front, becoming DARPA, but in those early days it was just ARPA, and its mission was essentially make sure the United States is never again caught off guard by a technological surprise. Fund the weird stuff, fund the long shots, fund the things that might not pay off for 20 years, but could change everything if they do. Here's the thing about ARPA that made it different from other government agencies. It was small, deliberately small, and it operated with an unusual amount of freedom. The people who ran its programs, program managers they were called, had real authority to direct funding toward ideas they believed in, without the usual layers of bureaucratic approval that slowed everything else in Washington to a crawl. And one of those program managers, a man named J.C.R. Licklider, would end up planting the seed that grew into the internet. Licklider is one of those figures who deserves to be far more famous than he is. He was a psychologist by training, not an engineer, not a computer scientist. He'd studied at Washington University in St. Louis and then at the University of Rochester, where he earned his PhD in psychoacoustics, the study of how humans perceive sound. He ended up at MIT in the 1950s, working on human factors research, which is basically the study of how people interact with machines. And it was at MIT that he first got his hands on a computer. Now, you have to understand what computers were like in the late 1950s. They were enormous. They filled entire rooms. They cost millions of dollars. And they were batch processing machines, which means you didn't sit down at a computer and use it the way you use your phone. Instead, you wrote your program out on punch cards, these stiff paper cards with holes punched in specific patterns. And you handed your stack of cards to an operator, and the operator fed them into the machine. And then you waited. Sometimes hours, sometimes overnight. And then you got your results back. And if you'd made a typo on one of your punch cards, if you'd put a comma in the wrong place, the whole thing failed and you started over. It was like trying to have a conversation with someone by mailing them letters and waiting days for a reply. Licklider looked at this situation and thought it was absurd. He could see that computers were going to become incredibly powerful, but he also saw that the way humans interacted with them was the bottleneck. In 1960, he wrote a paper called Man-Computer Symbiosis, and it's one of those documents that, reading it now, feels almost prophetic. He described a future where humans and computers would work together in real time, where the computer would handle the tedious calculation and data retrieval, and the human would handle the creative thinking and decision-making. He imagined people sitting at screens, interacting with information fluidly, the machine responding instantly. This was 1960. The idea of a personal computer was still 15 years away. The idea of the internet was barely a whisper. But Licklider could see it. In 1962, ARPA hired him to run their Information Processing Techniques Office, IPTO they called it. And this is where things start to get really interesting, because Licklider didn't just fund individual computer research projects. He started thinking about connecting computers together. He called his vision the Intergalactic Computer Network. And yes, he was being a little playful with the name, but the core idea was serious. He imagined a future where all the major research computers in the country could talk to each other, where a researcher at MIT could use a program running on a machine at Stanford, where data could flow between institutions as easily as a phone call. Think about what a radical idea that was. In 1962, every computer was an island. Each one had its own operating system, its own programming language, its own way of doing things. The notion that you could somehow link them all together into a coherent network, that was science fiction to most people. But Licklider started talking about it, writing memos about it, and most importantly, funding the people who might actually figure out how to do it. He didn't stay at ARPA long enough to see it built. He left in 1964. But the people he'd funded and inspired carried the idea forward, and one of those people was a man named Bob Taylor. Taylor is another one of those names that should be better known. He'd grown up in Texas, studied experimental psychology. There's that psychology connection again. These early internet pioneers thinking about humans first and machines second. And by 1966, he was running IPTO, the same office Licklider had led. And Taylor had a problem that perfectly illustrated why a computer network was needed. In his office at the Pentagon, Taylor had 3 different computer terminals, one connected to a machine at MIT, one connected to a machine at UC Berkeley, one connected to a machine at a research center in Santa Monica. And each terminal was completely different. Different commands, different login procedures, different everything. If he wanted to access all 3 machines, he had to learn 3 separate systems and physically walk between 3 different desks. It was ridiculous. And Taylor thought, what if all these computers could be connected to one network and you could reach any of them from a single terminal? So in February 1966, Taylor walked into the office of ARPA's director, Charles Hertzfeld, and pitched the idea. The conversation, by Taylor's own account, lasted about 20 minutes. Hertzfeld said yes and allocated $1 million to get it started. Just like that. No lengthy proposal process, no committee review. This is what made ARPA special. Decisions could happen fast, based on the judgment of smart people who understood the potential. But having the money and the mandate was one thing. Actually building the network was something else entirely. And this is where the real engineering challenge begins, because connecting computers together sounds simple in the abstract, but the details are devilishly complicated. You have to figure out how data gets from one machine to another. You have to figure out what happens when 2 machines try to send data at the same time. You have to figure out how to handle errors, because data gets corrupted in transit, electrical noise, interference. Just the basic physics of sending signals over long distances means that some of your ones are going to flip to zeros and vice versa. You need a way to detect that and fix it. And you have to figure out the most fundamental question of all. How do you route the data? If you've got, say, 15 computers scattered across the country, and computer A in Los Angeles wants to send a message to computer B in Boston, how does that message get there? Does it go directly on a dedicated line? Does it hop through intermediate machines? What if one of those intermediate machines is down? What if a line gets cut? This last question, the routing question, had a particular urgency in the 1960s that went beyond mere convenience. Remember, this was the Cold War. The military was deeply interested in communications networks that could survive an attack. The existing telephone network was centralized, calls were routed through switching centers, and if you knocked out a few key switching centers, the whole system could collapse. In a nuclear war, that meant the president might not be able to communicate with military commanders. The chain of command could be severed in the first few minutes of a conflict. A researcher at the Rand Corporation named Paul Baran had been thinking about exactly this problem. And in the early 1960s, he came up with an idea that was genuinely revolutionary, though it took years for people to appreciate it. Baran proposed what he called a distributed network. Instead of having a few central hubs that everything depended on, you'd have many nodes, each connected to several others, forming a web-like mesh. If any single node was destroyed, data could simply route around the damage, finding an alternate path through the mesh. It was resilient by design. You'd have to destroy a huge fraction of the network to actually bring it down. But Baran's really clever insight was about how data should travel through this network. Instead of establishing a dedicated connection between sender and receiver, the way a phone call works, where a circuit is opened and held for the duration of the conversation. Baran proposed breaking each message into small chunks. Each chunk would be labeled with its destination address and sent independently through the network. Different chunks of the same message might take different paths. When they arrived at the destination, they'd be reassembled into the original message. He called this message switching, using what he termed message blocks. Now, here's what's fascinating. At almost exactly the same time, completely independently, a British computer scientist named Donald Davies at the National Physical Laboratory in London was developing the same idea. Davies called his chunks packets. And it's his term, packet switching, that stuck. Two people, on opposite sides of the Atlantic, working on different problems, arriving at the same fundamental insight. Don't send messages whole. Break them into pieces. Think about why this is so clever. Imagine you're trying to move a house across the country. You could try to pick up the whole house and carry it, which requires an enormous truck and a clear, dedicated route the entire way. Or you could disassemble the house into numbered pieces, load them onto many smaller trucks, and let each truck find its own way to the destination. If one road is blocked, that truck takes a detour. If one truck breaks down, you only lose a few pieces, and you can send replacements. When everything arrives, you reassemble. That's packet switching, and it's the foundational idea that makes the internet possible. Taylor needed someone to actually build this network. He found Larry Roberts, a young computer scientist at MIT's Lincoln Laboratory, who had already done some early experiments in connecting computers over long-distance lines. Roberts was initially reluctant. He had a good thing going at Lincoln Lab. But Taylor, with ARPA's backing, applied some pressure. And by the end of 1966, Roberts had agreed to come to Washington and lead what would become the most consequential networking project in history. Roberts started designing the network in earnest in 1967, and almost immediately he ran into a political problem that was as thorny as any technical one. The plan called for connecting computers at major research universities, MIT, UCLA, Stanford, UC Santa Barbara, the University of Utah, and others. But the professors at these universities were not thrilled about the idea. They worried that connecting their expensive, carefully maintained research computers to a network would eat up processing power. They worried about security. They worried that researchers at other institutions would hog their machines. There was real resistance, and Roberts had to spend considerable energy just getting people to cooperate. The solution to the processing power concern was elegant. Instead of making each university's main computer handle all the networking tasks, the routing, the error checking, the protocol management, Roberts and his team decided to build a separate, dedicated computer at each site whose only job was to handle the network communication. They called these machines Interface Message Processors, or IMPs. The IMP would sit between the university's host computer and the network, handling all the messy details of packet switching so the host computer could go on doing its research work without being burdened. Think of the IMP as a translator and traffic manager sitting at the border between each site and the wider network. The contract to build the IMPs went to a small company in Cambridge, Massachusetts called Bolt Beranek and Newman, BBN. And this is where the rubber meets the road, because BBN had to take the theoretical ideas about packet switching and turn them into actual working hardware and software on a tight timeline, with technology that was primitive by today's standards. The IMPs were built from modified Honeywell DP516 mini computers, machines with just 12 kilobytes of memory. 12 kilobytes. The period at the end of this sentence, if you were to store it as a character in a text file, would take up 1 byte. These machines had 12,000 of those to work with, and they had to manage all the routing, error correction, and communication for a node on the network. The team at BBN, led by Frank Hart, worked through 1968 and into 1969, designing and building and testing. And by the late summer of 1969, the first IMP was ready to ship. It went to UCLA, where a young professor named Leonard Kleinrock had a team standing by to receive it. Kleinrock, it's worth noting, had done his doctoral dissertation at MIT on the mathematical theory of packet switching. He'd been thinking about how data flows through networks since the early 1960s, and now he was about to see the theory become reality. The IMP arrived at UCLA on September 1st, 1969. It was a refrigerator-sized machine, heavy enough that it took several people to maneuver it into place. Kleinrock's team connected it to their host computer, a Scientific Data Systems Sigma 7, and started testing. A month later, the second IMP arrived at the Stanford Research Institute in Menlo Park, about 350 miles up the California coast. And on October 29, 1969, a graduate student at UCLA named Charlie Klein sat down at a terminal and attempted to log into the machine at Stanford, remotely, over the network. He typed the letter L. It arrived at Stanford. He typed the letter O. It arrived. He typed the letter G, and the system crashed. The Stanford machine's software had a bug, and it choked. So the first message ever sent over what would become the internet was unintentionally just two letters, L-O, low, as in lo and behold. Kleinrock later joked that it was the most prophetic accident in the history of technology, a message of awe, transmitted at the exact moment a new age was beginning. They fixed the bug within an hour and completed the full login successfully. And just like that, two computers 350 miles apart were talking to each other through a packet-switched network. By the end of 1969, 4 nodes were online: UCLA, Stanford Research Institute, UC Santa Barbara, and the University of Utah. They called it the ARPANET. It was tiny, fragile, experimental, and almost nobody outside a small circle of researchers knew it existed. But the fundamental architecture was in place. Packets of data were flowing between machines, finding their routes, arriving and being reassembled. The thing actually worked. Now, making it work reliably, making it scale, making it talk to other networks that didn't exist yet. That was a whole different set of problems. And the people who tackled those problems were, for the most part, astonishingly young. The graduate students and junior researchers who wrote the first protocols for the ARPANET were in their 20s. They were inventing the rules of a new world, and they knew it. And there was this wonderful combination of seriousness and playfulness in how they went about it. They called themselves the Network Working Group, and when they started writing down their ideas for how the network should operate, they deliberately chose an informal format. A guy named Steve Crocker wrote the first one, dated April 7th, 1969, and he was so worried about seeming presumptuous, about seeming like he was trying to dictate standards to senior researchers, that he titled the document Request for Comments. Just a request, just asking for feedback. That naming convention stuck, and to this day, the technical standards that govern the internet are published as RFCs, Requests for Comments. There are now over 9,000 of them, and they define everything from how email works, to how video streams, to how your browser knows where to find a website, all because a 20-something graduate student was too polite to call his document a standard. He called it a request instead, and that spirit of humility, of open collaboration, of hey, here's an idea, what do you think, that became baked into the culture of how the internet was built. It's one of those small decisions that echoes for decades. And the RFCs themselves are fascinating documents if you ever stumble across them. They range from deeply technical specifications that would make your eyes glaze over to genuinely witty, almost literary pieces of writing. There's a long tradition of publishing joke RFCs on April 1st every year. One of them proposed a protocol for transmitting IP packets via carrier pigeon, and it was written with completely straight-faced technical language, complete with packet loss estimates due to hawks. But the serious ones, the the ones that actually shaped the network, those were hammered out through this collaborative process where someone would propose an idea, others would critique it, someone would write a better version, and gradually a consensus would emerge. No one was really in charge. There was no CEO of the internet. There was no board of directors voting on standards. It was just this loose, voluntary community of engineers and researchers who cared about making the thing work. And making it work meant solving some genuinely hard problems. Think about what you've got in late 1969, early 1970. You've got 4 computers connected by these IMPs, those refrigerator-sized interface message processors that BBN built. The IMPs handle the packet switching, the routing, the low-level mechanics of getting data from point A to point B. But that's just the plumbing. What do you actually do with it? How do 2 programs on 2 different computers, potentially built by different manufacturers running different operating systems, actually communicate in a meaningful way? That's the protocol problem, and it's the thing that consumed the network working group for the next several years. The first real protocol they developed was called NCP, the Network Control Protocol. It was finalized around 1970, and it became the standard way that host computers on the ARPANET talked to each other. NCP handled the basics, establishing connections, managing the flow of data so that a fast computer didn't overwhelm a slow one, breaking messages into manageable pieces. It worked. It worked well enough that the ARPANET started to grow. By 1971, there were 15 nodes. By 1972, there were 37. Universities and research labs across the country were getting connected, and once they were connected, people started building things on top of the network that nobody had originally planned for. Here's the thing that keeps happening in the history of the internet, and it's one of the most important patterns to understand. The people who build the infrastructure almost never predict the killer application. They build a road, and then someone invents the drive-through restaurant. They build a network for sharing computing resources and scientific data, and what actually takes off is electronic mail. Ray Tomlinson, an engineer at BBN, the same company that built the IMPs, sent the first network email in late 1971. He was working on a program that could send messages between users on the same computer, which was already a thing. And he thought, well, what if I could send a message to a user on a different computer across the network? It wasn't a big dramatic moment. He later said the first test messages were completely forgettable, something like QWERTYUIOP, just testing the keyboard. But he made one decision that you use every single day. He chose the @ sign, the little at symbol, to separate the user's name from the computer's name. Tomlinson at BBN, user at host. He picked it because it was the one character on the keyboard that was unlikely to appear in anyone's name. A tiny, practical decision. And now the @ symbol is probably one of the most typed characters in human history, recognized in virtually every language on Earth, all because one engineer needed a delimiter that wouldn't cause confusion. Email exploded on the ARPANET. Within a couple of years, it accounted for the majority of all network traffic. The network that had been built so that a physicist at UCLA could run a program on a computer at MIT was being used overwhelmingly for people to send each other messages. Some of those messages were work-related. A lot of them were not. People started mailing lists, group discussions about science fiction, about recipes, about politics. The ARPANET, this Cold War-funded research project, was becoming a social space, and the people running it mostly let it happen because they understood, intuitively or explicitly, that the value of a network comes from what people choose to do with it, not from what the designers intended. Now, while email was taking off and the ARPANET was growing across the United States, something else was happening that would turn out to be even more important in the long run. Other networks were being built, not copies of the ARPANET. Different networks, with different technologies, for different purposes. There were radio-based networks, like AlohaNet in Hawaii, which used radio waves instead of leased telephone lines to connect computers across the Hawaiian Islands. There were satellite networks. There were local area networks starting to appear inside individual buildings and campuses. And here's the problem. None of them could talk to each other. The ARPANET used NCP. AlohaNet used its own protocols. A satellite network had completely different constraints and requirements. If you were on the ARPANET, you could only communicate with other ARPANET machines. The network was a walled garden, even if nobody thought of it that way yet. This is where Bob Kahn enters the story, and shortly after, Vint Cerf, and together they tackle what might be the single most important engineering problem in this entire history. How do you connect networks to each other? Not computers to a network. That was the ARPANET problem, and it was solved. But networks to networks. How do you build a network of networks? An internetwork. An internet. Bob Kahn had come from BBN, where he'd worked on the original IMP design. By 1972, he'd moved to DARPA. The agency had added defense to its name by then. And he was thinking about this exact problem. He'd seen the ARPANET demonstration at a major computer conference in Washington, D.C. in October 1972, where they'd set up a working ARPANET node right in the conference hall and let attendees try it. It was a sensation, but Kahn was already thinking beyond it. He knew about the radio networks, the satellite experiments, and he could see that the future wasn't one network. It was many networks, and they needed to interoperate. So Kahn started sketching out the principles for what he called an open architecture network. The key insight, and this is really beautiful in its simplicity, was that you shouldn't try to make all networks the same. You shouldn't force every network to use the same internal protocols, the same hardware, the same speeds. Instead, you should create a common language that sits on top of all of them. Each network can work however it wants internally. But when it needs to send data to another network, it translates that data into the common language, sends it across, and the receiving network translates it back into whatever format it uses locally. It's like having a universal postal system. The mail trucks in France and the mail trucks in Japan can be completely different vehicles driving on different sides of the road, but as long as they agree on how to address an envelope and how to hand off a package at the border, the letter gets through. Kahn brought in Vint Cerf, who'd been one of those young graduate students in the original network working group at UCLA. He'd actually been involved in testing the very first ARPANET connection, the famous LO message. Cerf had moved to Stanford by then, and together, Kahn and Cerf spent months working through the design. In 1973 and 1974, they developed what they called TCP, the Transmission Control Protocol. They published a landmark paper in May 1974, a protocol for packet network intercommunication, and it laid out the architecture that would eventually become the Internet as we know it. Now, the original TCP tried to do everything in one protocol: reliable delivery, routing between networks, error checking, all of it. Over time, through years of testing and refinement and more RFCs and heated debates among engineers, it got split into two layers. TCP handled the reliability piece, making sure all the packets arrived, in order, without errors, reassembling them into the original message. and a new protocol called IP, the Internet Protocol, handled the addressing and routing piece, figuring out how to get each individual packet from its source network to its destination network, hopping through whatever intermediate networks it needed to cross. Together, they became TCP/IP, and that pair of protocols is still, right now, tonight, as you're lying here, the fundamental language of the Internet. Every single thing you do online, every website, every video call, every message, every software update, it all rides on TCP/IP, the design that Kahn and Cerf sketched out in the early 70s. But here's what's really clever, and what made it so enduring. TCP/IP was designed to be indifferent to the physical network underneath it. It doesn't care if your data is traveling over fiber optic cable, or copper wire, or radio waves, or a satellite link, or even, theoretically, those carrier pigeons from the joke RFC. As long as the network at each end can package data into IP packets and send them along, the system works. This is the principle of layering, separating what the network does from how the network does it physically, and it's one of the most powerful ideas in all of engineering. It means you can swap out the underlying technology without breaking the applications that run on top. It's why the Internet survived the transition from telephone lines to cable modems to fiber optics to cellular networks to Wi-Fi. The physical layer kept changing, but TCP/IP didn't care. It just kept working. The transition from NCP to TCP/IP on the ARPANET didn't happen overnight, though. It took years. There was resistance, there were compatibility headaches, there were machines that needed to be upgraded. DARPA finally set a hard deadline, January 1st, 1983. On that date, every machine on the ARPANET had to switch from NCP to TCP/IP, or it would simply stop being able to communicate. The engineers called it Flag Day, and it worked. It was messy in places, and some sites scrambled at the last minute, but on January 1st, 1983, the ARPANET became a TCP/IP network. Some people consider that date the true birthday of the Internet, not 1969, when the first message was sent, but 1983, when the protocol that actually defines the Internet was switched on. And something else happened in 1983 that solved a problem you might not have thought about yet, but once I describe it, you'll realize how fundamental it is. Think about IP addresses, those numerical labels that identify every device on the network. In the early ARPANET days, there weren't that many machines, so you could just keep a list. Literally, a text file. There was a single file called hosts.txt, maintained at the Stanford Research Institute, and it contained the name and address of every computer on the network. When the list changed, you downloaded a new copy. That worked fine when there were a few dozen hosts. But by the early 80s, the network was growing fast, and this approach was falling apart. The file was getting huge. It was constantly out of date, and there were naming conflicts. 2 different sites trying to use the same name. It was like trying to run a phone system where everyone keeps their own handwritten copy of the phone book, and nobody agrees on how to spell anybody's name. It was chaos waiting to happen, and by 1983, it had arrived. So a guy named Paul Makapetris, working at USC's Information Sciences Institute, proposed something elegant. Instead of one giant file that everyone has to copy, what if you built a distributed system, a hierarchy of name servers, each responsible for its own little piece of the naming universe? You'd break the namespace into chunks, delegate authority, and let each chunk manage itself. This became the domain name system, DNS. And it's one of those things that's so fundamental to how you use the internet today that it's almost invisible. Every single time you type a web address into your browser, every time your phone checks for new email, every time any app on any device reaches out to any server anywhere, DNS is working behind the scenes, translating human-readable names into the numerical IP addresses that the network actually uses. Here's how it works, and it's really quite beautiful in its simplicity. Imagine a tree. At the very top, you have the root. Below the root, you have what are called top-level domains, things like .com, .edu, .gov, .org, and eventually country codes like .uk and .jp. Below each of those, you have second-level domains. So under .com, you might have example in example.com, and below that, you can have subdomains, and subdomains of subdomains, branching out as far as you need. The genius is that no single authority has to know everything. The root servers know who's responsible for .com. The .com servers know who's responsible for example.com. And the servers for example.com know the specific addresses of the machines within that domain. So when your computer needs to find, say, mail.example.com, it starts at the top and works its way down, asking each level, hey, who handles the next piece? Each server only needs to know about its own branch of the tree, its delegation all the way down. Macapetris published the original DNS specifications in 1983, RFC 882 and RFC 883, and the system was operational by 1984. And think about what this meant. Suddenly, the network could grow without anyone needing to maintain a master list. You could add new domains, new machines, new entire organizations, and as long as each piece of the hierarchy did its job, the whole thing just worked. It scaled. That word, scaled, comes up over and over in the history of the internet, because almost every major innovation was really about solving a scaling problem. The network kept growing faster than anyone expected, and every few years, some piece of the infrastructure that had been working fine would start to buckle under the weight, and someone would have to invent a new solution. DNS was one of those solutions, and it's still running today, handling billions of queries every day, still using fundamentally the same hierarchical design Macapetris laid out in 1983. Now, around this same period, the early to mid-80s, something else was happening that would turn out to be enormously important, even though it didn't look like much at the time. Local area networks were exploding. Remember, the ARPANET connected big research institutions over long distances, but inside those institutions, people were starting to connect their own computers together on smaller local networks. Ethernet, which Bob Metcalfe had invented at Xerox PARC back in 1973, was becoming commercially available. And it was fast, at least by the standards of the day. These local networks were popping up everywhere, in universities, in corporations, in government labs. And because TCP/IP was designed to work across different kinds of networks, these LANs could connect to each other and to the wider internet. The number of connected machines started climbing not just steadily, but exponentially. And this is where the National Science Foundation enters the story in a big way. By the mid-80s, the ARPANET was still primarily a defense research network. If you were at a university that had a DARPA contract, great, you could get on. But there were hundreds of universities and research institutions that didn't have that connection, and they wanted in. They could see what the connected researchers were doing, sharing data, collaborating across distances, sending email, and they wanted that too. So in 1986, the NSF built something called NSF-Net. It was a backbone network, a high-speed spine connecting 5 supercomputer centers across the country at Cornell, Princeton, the University of Illinois, Carnegie Mellon, and the University of California, San Diego. The initial backbone ran at 56 kilobits per second, which is laughably slow by today's standards, slower than a dial-up modem from the 90s. But it was a start. And more importantly, regional networks could connect to it. And through those regional networks, universities all over the country could finally get online. Here's the thing about NSF-Net that really mattered. It wasn't just a technical achievement, it was a policy decision. The NSF had an acceptable use policy that restricted the backbone to research and education traffic. No commercial use. That might sound limiting, but what it actually did was create a massive, publicly funded network infrastructure that connected the academic world. And the academic world, it turns out, is really good at building things on top of infrastructure. Researchers started developing tools, sharing software, creating information repositories. The culture of openness that had started with those early RFCs on the ARPANET, that culture of sharing, of building on each other's work, it spread to a much wider community. By 1988, NSF-Net had been upgraded to T1 speeds, 1.544 megabits per second, about 28 times faster than the original backbone. By 1991, it was upgraded again to T3, 45 megabits per second. The growth was staggering. In 1986, the network had a few thousand hosts. By 1989, it had over 100,000. By 1992, over 1 million. Every time the infrastructure got faster, people found new things to do with it, which attracted more people, which demanded faster infrastructure. It was a virtuous cycle, and it was accelerating. But let's slow down for a moment, because something was happening in this period that doesn't get talked about enough. The internet in the late 80s was powerful, but it was also, and I say this with love, kind of a mess to actually use. If you wanted to find information on a remote computer, you had to know where it was, what protocol to use, and often the exact commands to retrieve it. There were tools, FTP for transferring files, Telnet for logging into remote machines. But there was no unified way to just browse around and discover things. It was like having a library with millions of books, but no catalog, no shelving system, and no librarian. You had to already know what you were looking for and where it was. People tried to fix this. In 1991, a team at the University of Minnesota created something called Gopher. And Gopher was actually really good. It organized information into hierarchical menus. You'd connect to a Gopher server and see a list of topics. Click on one, get a submenu, drill down until you found what you wanted. It was text-based, clean, and intuitive. Gopher spread fast across universities. For a brief moment, it looked like Gopher might be the way people would navigate the internet forever. But also, in 1991, halfway around the world, something else was taking shape. At CERN, the European Particle Physics Laboratory in Geneva, Switzerland, a British computer scientist named Tim Berners-Lee had been working on a different approach to the same problem, and his approach was going to change everything. Berners-Lee's insight was rooted in something he'd been thinking about for years. Back in 1980, he'd written a little program for himself called Inquire, which let him create links between different pieces of information. Not hierarchical menus, but a web of connections. Any document could link to any other document, regardless of where it was stored. He was influenced by an old idea, actually, one that went all the way back to 1945, when Vannevar Bush had written an essay called As We May Think, describing a hypothetical device called the Memex that would let users follow associative trails through vast libraries of information. And Ted Nelson, in the 1960s, had coined the term hypertext for exactly this kind of linked, non-linear writing. But nobody had built a working networked hypertext system at global scale. Berners-Lee decided to try. And what he created wasn't just one thing. It was a whole interlocking set of things. He designed a protocol for transferring hypertext documents over the network, HTTP, the Hypertext Transfer Protocol. He created a language for writing those documents, HTML, the Hypertext Markup Language, which let you embed links right in the text. And he created a naming scheme for locating resources anywhere on the internet, the URL, the Uniform Resource Locator, protocol, language, and addressing. 3 pieces that fit together into a system he called the World Wide Web. He built the first web server, running on a Next computer at CERN. He built the first web browser, and on August 6, 1991, he posted a summary of the project to a news group, making it available to anyone who wanted to try it. The first website in history was info.cern.ch, and it described the World Wide Web project itself, what it was, how to use it, how to set up your own server. It was modest, almost comically understated for something that would reshape civilization. And for a while, it grew slowly. Most people in the internet community were still using Gopher, or FTP, or email. The web was just one more tool among many. But Berners-Lee had made a decision early on that would prove to be absolutely transformative. He gave it away. He made the web's protocols, its specifications, its code, all of it, free, open. No patents, no licensing fees, no royalties. Anyone could build a web server. Anyone could write a web page. Anyone could create a browser. And this wasn't some default outcome. It was a fight. CERN could have tried to own the web the way companies owned proprietary software. There were people who thought they should, but Berners-Lee pushed hard for openness. And in April 1993, CERN formally released the World Wide Web technology into the public domain. No strings attached. Think about what that means. Imagine if one organization had owned the web. If every time you built a website, you had to pay a licensing fee. If every browser had to negotiate terms. The web would have become like cable television, a walled garden controlled by whoever held the intellectual property. Instead, it became a commons. And that single decision, more than any line of code Berners-Lee ever wrote, is arguably why the web exploded the way it did. But even free technology needs a spark to catch fire, and for the web, that spark came from a place you might not expect. The National Center for Supercomputing Applications at the University of Illinois at Urbana-Champaign. NCSA. The same kind of supercomputing center that NSFNet had been built to connect. And the person who lit that spark was a 22-year-old undergraduate named Marc Andreessen. Andreessen was working at NCSA as a student programmer, and he'd been playing around with the web. He thought it was fascinating, but frustrating. Berners-Lee's original browser, the one he'd built on the Next machine, was actually quite sophisticated. It could display formatted text, images. You could even edit pages right in the browser. But it only ran on Next computers, which almost nobody had. The browsers available for regular Unix workstations and PCs were clunky, text-based, hard to use. Andreessen looked at this situation and thought, what if there were a really good browser? One with a graphical interface, one that was easy to install, one that could show images right there in the page mixed in with the text, one that ran on all the platforms people actually used. So he and a colleague named Eric Bina started building one. They worked obsessively, long nights, weekends, the kind of focused sprint that young programmers are famous for. And in early 1993, they released Mosaic. It ran on Unix first, then on Windows and Macintosh, and it changed everything. Here's the thing about Mosaic. It wasn't technically revolutionary in the way that TCP/IP was revolutionary, or the way packet switching was revolutionary. What it did was make the web accessible. It made the web visual. Before Mosaic, using the web felt like using a command line tool. After Mosaic, it felt like flipping through a magazine. You could see images in line with text. You could click on blue underlined links and jump to another page. The back button worked. It had bookmarks. It was intuitive in a way that no previous internet tool had been, and it was free to download. The effect was staggering. Web traffic, which had been growing steadily but modestly, went vertical. In 1993, web traffic on the NSFNET backbone increased by something like 341,000%. That's not a typo. 341,000% in a single year. Mosaic was being downloaded by the thousands, then tens of thousands. Universities, businesses, hobbyists, everyone was suddenly putting up web pages. The web went from being one of many internet services to being the internet, at least in the public imagination. And this is where the story starts moving really fast. So let's slow down for a second and appreciate what had to be true for this moment to happen. You needed packet switching, which Baran and Davies figured out in the early 60s. You needed a working network, which ARPANET proved in 1969. You needed internet working protocols, which Kahn and Kerf built through the 70s. You needed the domain name system, which Maka Petris designed in 1983. You needed cheap local networking, which Metcalfe's Ethernet provided. You needed a public backbone, which NSF funded. You needed the web's three interlocking inventions, HTTP, HTML, URLs, which Berners-Lee created. You needed the decision to make it all free. And then you needed someone to build a browser that regular people could actually use. Every single one of those layers had to exist before the web could take off. Remove any one of them, and the story stalls. That's 30 years of accumulated engineering, 30 years of decisions made by people who mostly couldn't have imagined what their work would eventually enable. Now, Andreessen graduated from Illinois in December 1993, and he moved to California. And almost immediately, he connected with a man named Jim Clark, who had founded Silicon Graphics, a company that made high-end graphics workstations. Clark was looking for his next venture, and he saw the web the way Andreessen did, as something enormous that was just getting started. In April 1994, they founded a company. It was originally called Mosaic Communications, but the University of Illinois objected to the use of the name Mosaic, so they changed it. They called it Netscape. Netscape Navigator launched in December 1994, and it was Mosaic but better, faster, more polished, with support for more of the emerging web standards. Netscape gave the browser away free to individuals and educational institutions and charged businesses for it. And it worked. By 1995, Netscape had something like 80% of the browser market. When Netscape went public on August 9th, 1995, its stock was supposed to be offered at $14 a share. They bumped it to $28 at the last minute. It opened at $71. By the end of the first day of trading, it closed at $58 and change, giving the company a market valuation of nearly $3 billion. The company was barely a year old. It had never turned a profit. Marc Andreessen, 24 years old, was on the cover of Time magazine, barefoot, sitting in a golden chair. This was the moment the broader world woke up to the internet. Not the research community, not the early adopters, not the Unix hackers, the general public, Wall Street, your neighbors. The Netscape IPO is often cited as the starting gun of the dot-com era, and for good reason. It proved that the internet wasn't just an academic curiosity, it was a business, a potentially enormous business. And this is also the moment Microsoft woke up. Bill Gates, to his credit, had been relatively slow to see the web coming. Microsoft was the dominant software company in the world. Windows was on almost every personal computer, and Gates had been focused on proprietary online services. Microsoft Network, MSN, which was supposed to be a competitor to services like CompuServe and America Online. The open web wasn't really on his radar. But when Netscape took off, Gates pivoted with a speed that was genuinely impressive and, depending on your perspective, genuinely terrifying. In December 1995, he gave a speech and released a memo called The Internet Tidal Wave, declaring that the internet was now Microsoft's highest priority. And then, Microsoft did what Microsoft did best in that era. It competed ferociously. They built Internet Explorer. The first version was rough, but Microsoft iterated fast. They bundled Internet Explorer with Windows, which meant that every person who bought a PC got a browser for free, already installed. You didn't have to download anything. You didn't have to know what a browser was. It was just there. And this is where things got ugly, because what followed was the browser wars. A period from roughly 1995 to about 2001, where Netscape and Microsoft fought for control of how people experienced the web. The technical consequences were real and messy. Both companies started adding proprietary extensions to HTML, features that only worked in their browser. Netscape had the blink tag. Microsoft had the marquee tag. Both added their own versions of dynamic content, scripting languages, layout features. Web developers started putting badges on their sites, best viewed in Netscape Navigator, or best viewed in Internet Explorer. The open web, the thing Berners-Lee had given away for free, was in danger of fragmenting into incompatible camps. It was like the internet working problem all over again, but at the application layer. Microsoft's bundling strategy worked. Internet Explorer's market share climbed steadily, from single digits in 1995 to over 50% by 1998 to over 90% by 2002. Netscape crumbled. The company was acquired by AOL in 1999 for about $4 billion, which sounds like a lot until you realize the browser that had once dominated the web was essentially dead as a competitive product. But before it died, Netscape did one last remarkable thing. In 1998, they released the source code of their browser to the public, creating the Mozilla Project. That open source code would eventually, years later, become Firefox. So even in defeat, the open web found a way to survive. But let's zoom out from the browser wars for a moment, because while Netscape and Microsoft were fighting over how you viewed web pages, something even more fundamental was happening underneath. The internet was being privatized. Remember NSFNet and its acceptable use policy? No commercial traffic on the backbone. That rule had been slowly eroding throughout the early 90s as commercial internet service providers, ISPs, built their own networks and interconnected with each other. Companies like UUNet, PSINet, SprintLink, they were building commercial backbone infrastructure in parallel with the government-funded one. And the traffic was shifting. By the mid-90s, most internet traffic was flowing over commercial networks, not NSFNet. the government backbone was becoming redundant. So on April 30th, 1995, NSFNet was officially decommissioned. The backbone was shut down. The internet was handed over, in a sense, to the private sector. Instead of one government-funded backbone, you now had multiple commercial backbones run by competing companies, all interconnecting at exchange points, network access points, or NAPs, that NSF had helped establish. It was a quiet transition, barely noticed by the public, but it was enormous. The internet went from being a government research project to being a commercial infrastructure, and that shift made possible everything that came next. The dot-com boom, e-commerce, streaming, social media, all of it. Because once commercial traffic was not just allowed but expected, the incentives changed completely. There was money to be made, and money, whatever else you think about it, is an extraordinarily powerful engine for building things fast. And build they did. Between 1995 and 2000, the amount of fiber optic cable laid under the ground and under the oceans was staggering. Companies like WorldCom, Global Crossing, Level 3, they raised billions of dollars and spent it on infrastructure, digging trenches, laying cable, lighting up fiber with the latest dense wavelength division multiplexing technology, which let you send multiple signals down a single fiber strand by using different colors of light. Each color carried its own data stream, and as the technology improved, you could pack more and more colors onto a single fiber. The bandwidth available on long-haul routes doubled, then doubled again, then again. It felt limitless. And meanwhile, at the other end of the connection, in people's homes, access was changing too. Through most of the 90s, if you wanted to get online at home, you used a dial-up modem. You plugged your computer into your phone line, your modem dialed a number, and you heard that sound, that iconic screech and hiss of two modems negotiating a connection. If you're old enough to remember it, you can probably hear it right now. That sound was actually meaningful, by the way. The modems were testing the phone line, figuring out what speeds it could support, agreeing on a protocol. It was a handshake, translated into audio. And the speeds were, by modern standards, almost comically slow. In the early 90s, 14.4 kilobits per second was standard, then 28.8, then 33.6, then 56K, which was the theoretical maximum for a standard voice phone line, and even that you rarely actually achieved in practice. Downloading a single photograph could take minutes. Downloading a song could take an hour. Streaming video was essentially out of the question. You simply could not push enough data through a 56K modem to deliver moving images in real time. A single frame of decent video might be hundreds of kilobytes, and you needed 30 of those every second. The math just didn't work. So the web in the mid-90s was mostly a text and images world, and even the images loaded slowly, painting themselves onto your screen line by line from top to bottom, like a very patient Polaroid developing before your eyes. But here's the thing. People knew broadband was coming. The technology existed. It just hadn't reached most homes yet. And the two paths it would take to get there were already being laid, quite literally, by two industries that had spent the previous century wiring up America for entirely different purposes. On one side, you had the telephone companies, the descendants of Alexander Graham Bell's empire, who had copper phone lines running to virtually every home in the country. On the other side, you had the cable television companies, who had their own parallel network of coaxial cables snaking into living rooms. Both of those networks had been designed for analog signals. Voice in one case, television in the other. But both could be repurposed to carry digital data at speeds that would make dial-up look like sending messages by carrier pigeon. The telephone company's approach was called DSL, digital subscriber line. And the core insight behind DSL was beautifully simple. Your phone line could actually carry a much wider range of frequencies than a normal voice call used. A voice call only needed a narrow slice of the available bandwidth, roughly the frequencies between 300 and 3,400 Hz, which is enough to make human speech intelligible. But the copper wire itself could handle frequencies up to about a megahertz or more. All that extra capacity was just sitting there, unused, wasted. DSL exploited it by splitting the line into channels. The low frequencies still carried your voice call, and the higher frequencies carried data. You could literally talk on the phone and surf the web at the same time, which felt like magic after years of dial-up monopolizing your phone line when anyone calling your house got a busy signal because you were on the internet. The cable companies had a different advantage. Coaxial cable was inherently a fatter pipe than twisted pair telephone wire. It had been designed to carry dozens of television channels simultaneously, each one a stream of analog video, which is a lot of data. The cable industry developed a standard called DOCSIS, Data over Cable Service Interface Specification, which carved out some of that channel capacity for internet data. Your cable modem would tune into a specific frequency on the cable, just like a TV tuner, except instead of a sitcom, it was receiving packets of internet data. Both approaches started rolling out to consumers in the late 90s, and the speeds were transformative. Early DSL and cable modems offered somewhere between 256 kilobits per second and 1.5 megabits per second downstream. That might not sound like much now, but compared to a 56K modem, even the low end was roughly 5 times faster, and the high end was almost 30 times faster. And crucially, these were always-on connections. No more dialing in, no more waiting for the handshake, no more getting kicked off when someone picked up the phone. You turned on your computer and you were just connected, already there. That shift, from dial-up to always-on, changed people's relationship with the internet in ways that are hard to overstate. The internet stopped being a place you visited and started being a place you lived. And that mattered enormously for what was about to happen, because the late 90s were the years of the dot-com bubble, and the always-on, increasingly fast internet was the oxygen that fed the fire. Now, the dot-com boom is one of those stories that looks obvious in hindsight. Of course it was a bubble. Of course most of those companies were going to fail. But living through it, the excitement felt rational. Or at least, it felt rational enough. The internet really was changing everything. E-commerce really was going to be huge. The logic was sound. It was the timing and the valuations that were insane. Let's talk about what was actually being built during this period, because not all of it was nonsense. Amazon launched in July 1995, initially as an online bookstore, operating out of Jeff Bezos's garage in Bellevue, Washington. Bezos had been working at a hedge fund in New York and had come across a statistic that web usage was growing at something like 2,300% per year. He made a list of 20 products that could be sold online and settled on books because the catalog was enormous, far too large for any physical store to stock, and books were standardized so customers knew exactly what they were getting. That logic was impeccable, and it worked. But Bezos always intended Amazon to be much more than a bookstore. He called it the everything store from the beginning. eBay launched around the same time, September 1995, founded by Pierre Omidyar. The legend is that he built it to help his fiancée trade Pez dispensers, which is a charming story that eBay's own PR team promoted for years, though Omidyar later admitted it was somewhat embellished. What eBay actually demonstrated was something profound: that the internet could create markets between strangers. Two people who would never have found each other in the physical world could now buy and sell with reasonable confidence, mediated by a reputation system. That was a genuinely new thing in the world. And then there was Google. Larry Page and Sergey Brin were graduate students at Stanford in 1996 when they started working on a search engine called Backrub, which is possibly the worst name in the history of technology. But the idea behind it was brilliant. Existing search engines like AltaVista and Yahoo ranked pages based mostly on the content of the page itself. How many times did your search term appear? Where did it appear? Things like that. Page and Brin realized you could treat the entire web like an academic citation network. If a lot of other pages linked to your page, that was like getting cited by other researchers. It meant your page was probably important. And if the pages linking to you were themselves important, that counted even more. They called this insight PageRank, a pun on Larry Page's name, and it produced search results that were dramatically better than anything else available. Google incorporated in September 1998, and within a couple of years it was clearly the best search engine on the web. Not the flashiest, not the most feature-rich. Google's homepage was famously, almost aggressively minimal, but the most useful. You typed in what you wanted, and Google found it. That simplicity was deceptive. Behind it was an enormous engineering challenge, crawling billions of web pages, indexing them, and returning relevant results in fractions of a second. Google built its own infrastructure from the ground up, famously using racks of cheap commodity hardware rather than expensive servers, and developing custom software to distribute work across thousands of machines. That approach, using massive numbers of ordinary computers working in parallel rather than a few powerful ones, would become one of the defining architectural patterns of the modern internet. But for every Amazon or Google, there were hundreds of companies that made no sense at all. Pets.com, which tried to sell pet food online and spent a fortune on a Super Bowl ad featuring a sock puppet, burned through $300 million and lasted barely 2 years. Webvan promised to deliver groceries to your door and raised over $800 million before collapsing. Cosmo.com would deliver a single DVD or a candy bar to your apartment for free. Their business model was essentially lose money on every transaction and make it up in volume, which is not actually how math works. The stock market didn't care. The Nasdaq Composite Index, which was heavy on tech stocks, climbed from around 1,000 in 1995 to over 5,000 by March of 2000. Companies with no revenue, no profits, and sometimes no coherent business plan went public and saw their stock prices double on the first day of trading. The metric that mattered wasn't earnings. It was eyeballs. How many people visited your website? The assumption was that if you got enough users, you'd figure out how to make money later. Sometimes that assumption turned out to be correct, but mostly it didn't. And then, in March 2000, the bubble burst. The Nasdaq peaked on March 10th at 5,048, and then it started falling. And it kept falling. By October 2002, it had dropped to around 1,139, a decline of nearly 80%. Trillions of dollars in market value evaporated. Hundreds of dot-com companies went bankrupt. Office parks in Silicon Valley emptied out. The Aeron chair, which had become the unofficial throne of the dot-com era, started showing up in bulk at used furniture stores. But here's what's really important to understand about the crash. The bubble was a financial phenomenon, not a technological one. The underlying technology, the internet itself, the web, the protocols, the fiber optic infrastructure, all of that survived. In fact, the overbuilding of fiber during the bubble years meant there was an enormous surplus of bandwidth available at rock-bottom prices after the crash. Companies that survived, Google, Amazon, eBay, and a new generation of startups that would emerge in the following years, inherited an infrastructure that was far more capable than what they needed, and they could lease it cheaply. The bust actually made the next wave of innovation cheaper and faster, and that next wave was already stirring, even in the wreckage of the crash, because something had shifted in how people thought about the web. The first generation of websites had been mostly static, pages that someone created and you read, like a digital magazine or brochure. But a new idea was forming, one that would eventually get a name, a somewhat annoying name, but a useful one. People started calling it Web 2.0, and the core idea was that the web could be a platform where users themselves created the content, not just reading, but writing, not just consuming, but participating. The web could be a conversation, not a lecture, and the technical foundations for that shift were already in place. A technology called AJAX, asynchronous JavaScript and XML, was making web pages feel more like applications. Instead of clicking a link and waiting for a whole new page to load, AJAX let the browser communicate with the server in the background, updating just part of the page without a full reload. Google Maps, which launched in February 2005, was one of the first applications to really show what this could do. You could grab the map and drag it, and new tiles would load seamlessly as you moved. It felt fluid, responsive, alive. It felt like software, not a web page. And that distinction between a web page and a web application was about to become one of the most important shifts in the entire history of the internet. Because once you stop thinking of the browser as a window for reading documents and start thinking of it as a place where you run software, everything changes. Your browser becomes an operating system of sorts. The applications you use every day, your email, your word processor, your spreadsheet, your photo editor, they don't need to live on your hard drive anymore. They can live on a server somewhere, and you just access them through your browser. And that idea, which sounds so obvious now, was genuinely radical in 2004 and 2005. Think about what Gmail did when it launched on April 1st, 2004. And yes, people actually thought it was an April Fool's joke, partly because of the date and partly because of the storage offer. Google said they'd give every user a full gigabyte of free email storage. At the time, Hotmail was offering something like 2 megabytes. Yahoo was in the same ballpark. A gigabyte was 500 times more than what the competition offered, and it seemed absurd, almost impossible. But Google had figured out something crucial. Storage was getting cheaper faster than people realized, and if you could build your infrastructure on thousands of cheap commodity servers instead of a few expensive ones, the economics worked out differently than everyone assumed. So, Gmail launched with a gigabyte of storage, a fast and fluid AJAX interface that let you search your email instantly instead of clicking through folders, and threaded conversations that grouped replies together. It felt like the future. And it was invitation only at first, which created this incredible demand. People were literally selling Gmail invitations on eBay. But here's what mattered more than any single feature. Gmail proved that a web application could be as good as, maybe better than, desktop software. You didn't need to install anything. You didn't need to worry about which computer you were sitting at. Your email was just there, in the cloud, accessible from anywhere. And that word, cloud, was starting to creep into the vocabulary, though it wouldn't become ubiquitous for a few more years. Now, Gmail was one piece of a much larger puzzle. Let's talk about what else was happening in this Web 2.0 moment, because it wasn't just about better technology. It was about a philosophical shift in who the internet was for and what people did with it. In February 2004, just 2 months before Gmail launched, a Harvard sophomore named Mark Zuckerberg opened a website called The Facebook to his fellow students. The basic idea wasn't new. There had been social networking sites before. Friendster launched in 2002, and MySpace in 2003, and both had attracted millions of users. But Facebook did something subtly different. It started with a closed community. You needed a Harvard email address to sign up, and then expanded slowly, university by university. This created a sense of trust and authenticity that the open-to-everyone platforms didn't have. People used their real names. They posted real photos. The social graph, as it came to be called, the map of who knows whom, was built on actual relationships, not anonymous handles. And then there was YouTube, founded in February 2005 by 3 former PayPal employees, Chad Hurley, Steve Chen, and Jawed Karim. Before YouTube, putting video on the internet was a nightmare. You had to deal with competing video formats, codec downloads, buffering issues, and hosting costs that could bankrupt you if something went viral. YouTube solved all of that with a simple upload button and a Flash-based video player that worked in any browser. The first video ever uploaded was Karim standing in front of elephants at the San Diego Zoo, 18 seconds long, posted on April 23, 2005. It's still there, by the way. Within a year, YouTube was serving 100 million video views per day. Google bought it in October 2006 for $1.65 billion, which seemed like an insane amount of money at the time and turned out to be one of the greatest bargains in business history. So think about what happened in just this narrow window, 2004 to 2006. Gmail, Facebook, YouTube, along with Flickr for photos, Dell.icio.us for bookmarks, Digg for news. All of them shared the same DNA. They were platforms where ordinary people created the content. The value didn't come from what the company published. It came from what the users uploaded, shared, wrote, and linked to. The company provided the stage. The users provided the show. And here's the thing that made all of this possible on a technical level, something we should really talk about, because it's one of those invisible layers that changed everything without most people ever knowing it existed. By the mid-2000s, a set of practices had emerged for building internet infrastructure at massive scale, and they were fundamentally different from how the old enterprise world worked. Instead of buying one enormous, expensive server from Sun Microsystems, or IBM, and hoping it didn't fail, companies like Google built their systems on thousands of cheap machines, regular commodity hardware, the kind of stuff you could buy at any electronics store, and then wrote software that assumed individual machines would fail constantly. The genius was in the software layer. If one machine died, the system automatically routed around it. Data was replicated across multiple machines in multiple locations, so nothing was ever stored in just one place. This approach had a name that would become one of the defining concepts of modern computing: cloud computing. And while the term gets thrown around loosely, the core idea is precise and powerful. Instead of buying and maintaining your own servers, you rent computing power, storage, and services from someone who runs enormous data centers. You pay for what you use, like electricity. You scale up when you need more, scale down when you don't. Amazon, of all companies, was the one that really commercialized this. In March 2006, Amazon launched Amazon Web Services, AWS, starting with a simple storage service called S3, followed a few months later by EC2, which let you rent virtual servers by the hour. Jeff Bezos had realized that the infrastructure Amazon built to handle its holiday shopping peaks sat mostly idle the rest of the year, and that other companies needed the same kind of scalable infrastructure. So Amazon started renting out its excess capacity, and in doing so, accidentally created what would become one of the most profitable businesses in the history of technology. The impact of cloud computing on the internet is hard to overstate. Before AWS and its competitors, Google Cloud, Microsoft Azure, which came later, starting an internet company required significant upfront investment in hardware. You had to buy servers, find a place to put them, hire people to maintain them, and guess how much capacity you'd need. If you guessed wrong, you either wasted money on idle hardware or your site crashed under unexpected traffic. Cloud computing eliminated that entire problem. A couple of people with laptops and a credit card could now build and launch a service that scaled to millions of users. The barrier to entry for internet innovation dropped to nearly zero, and that's why the late 2000s and 2010s saw an explosion of startups that would have been impossible a decade earlier. Instagram launched with 13 employees. WhatsApp had 55 engineers when it was serving hundreds of millions of users. They could do this because they were running on Amazon's infrastructure, not their own. Now, there's another thread we need to pick up here, because while all of this was happening on the software and services side, something equally transformative was happening in your pocket. And that story really begins on January 9th, 2007, when Steve Jobs walked onto a stage in San Francisco and said he was introducing 3 products: a widescreen iPod, a revolutionary mobile phone, and a breakthrough internet communicator. And then he repeated those 3 things, and repeated them again, and the audience slowly realized he was talking about one device: the iPhone. Now, smartphones existed before the iPhone. BlackBerry had been around since the late 90s, and it was huge in the business world. People called them crackberries because they were so addictive. Palm had the Trio. Nokia had various smartish phones. But all of these devices treated the internet as a secondary feature, something you could kind of access in a limited way through a stripped-down browser on a tiny screen. The iPhone changed the expectation. It had a real web browser, Safari, that rendered actual web pages, not simplified mobile versions. You could pinch to zoom, scroll with your finger, tap links. It was the real internet in your hand. But the truly revolutionary moment came a year later, in July 2008, when Apple launched the App Store alongside the iPhone 3G. Suddenly, anyone could write software for this pocket computer and distribute it to millions of people through a single storefront. Google followed almost immediately with the Android market, later renamed Google Play, for phones running its Android operating system, which had launched in September 2008 on the HTC Dream. And within just a couple of years, the smartphone ecosystem exploded. By 2012, there were over 1 billion smartphones in use worldwide. By 2016, more people accessed the internet through mobile devices than through desktop computers. Think about what that means. The internet went from something you sat down at a desk to use, to something that was with you every waking moment, in your pocket, always connected, always on. And this shift, the mobile shift, changed the internet in ways that are still playing out today. It changed how applications were designed, because now you had to think about small screens and touch interfaces and intermittent connectivity. It changed business models, because mobile apps could charge small amounts through app stores in ways that web-based services struggled to do. It changed social dynamics, because now you could post a photo or a status update or a video from anywhere, instantly. The smartphone turned every person with a phone into a broadcaster, a photographer, a journalist, a cartographer. It democratized creation in a way that even Web 2.0 hadn't fully achieved. But it also concentrated power in ways that were starting to worry people. Because as the 2010s unfolded, a pattern became unmistakable. The Internet, which had been designed as a decentralized network where no single node was essential, had somehow produced the most centralized concentration of power in economic history. By the middle of the decade, the 5 most valuable public companies in the world were Apple, Google's parent company, Alphabet, Microsoft, Amazon, and Facebook. All of them were internet companies, or had become internet companies, and their dominance wasn't just financial, it was architectural. If you wanted to reach people on mobile, you essentially needed to go through Apple or Google. If you wanted to sell things online, Amazon was increasingly the default. If you wanted to advertise, Google and Facebook controlled the majority of digital ad spending. If you wanted cloud infrastructure, Amazon, Microsoft, and Google were the big 3. And this concentration had consequences that went far beyond business competition, because these platforms weren't just selling products, they were shaping how billions of people communicated, got their news, formed opinions, and understood the world. And the algorithms that determined what you saw in your Facebook newsfeed, or which YouTube videos were recommended next, or which Google search results appeared first. Those algorithms were optimized for engagement, for keeping you on the platform as long as possible. And it turned out that what keeps people engaged isn't always what's good for them or good for society. Outrage keeps people engaged. Misinformation, if it's sensational enough, keeps people engaged. Conspiracy theories keep people engaged. And the platforms, at least initially, had very little incentive to solve that problem, because engagement meant advertising revenue, and advertising revenue meant everything. Billions of dollars, quarter after quarter, flowing in because the machine was working exactly as designed. And that's the thing you have to understand. It wasn't a bug. It wasn't some unintended side effect that nobody saw coming. The algorithms were doing precisely what they were built to do. They were maximizing the metric they'd been told to maximize. The problem was that the metric was wrong, or at least it was incomplete. It measured attention without measuring harm. And for a while, through the early and mid-2000s, the consequences of that were mostly abstract. Researchers and critics pointed out the problems, but the platforms were still riding an enormous wave of public goodwill. Facebook was connecting old friends, helping people organize community events, letting grandparents see photos of grandchildren across the country. YouTube was democratizing video. Anyone with a camera could become a creator, could build an audience, could make a living. Google was organizing the world's information. These were genuinely useful things, and the darker dynamics were easy to dismiss as edge cases, as the cost of doing business at scale. But then came 2016, and the edge cases stopped feeling like edge cases. The US presidential election that year became a kind of inflection point for how people understood the power of platforms. Researchers discovered that fake news articles, completely fabricated stories, many of them originating from content farms in places like Veles, North Macedonia, where teenagers had figured out that sensational political content generated enormous advertising revenue through Facebook shares. These fake stories were generating more engagement on Facebook than real news from established outlets. That's a staggering thing to sit with. Made-up stories, designed purely to provoke clicks, were being seen and shared more widely than actual journalism. And Facebook's algorithm was facilitating it. because the algorithm didn't know the difference between a carefully reported investigation and a completely fabricated headline. It just knew which one got more clicks. And it wasn't just fake news. There was the Cambridge Analytica scandal, which broke wide open in early 2018 when reporting revealed that a political consulting firm had harvested personal data from tens of millions of Facebook users. Estimates ranged up to 87 million profiles, through a personality quiz app that exploited Facebook's data sharing policies. The data had been used to build psychological profiles and target political advertising with unprecedented precision. Facebook had known about the data harvesting since at least 2015, but hadn't disclosed it publicly. When the story broke, it triggered a global reckoning. Mark Zuckerberg was called to testify before the US Congress and the European Parliament. Facebook's stock dropped by over $100 billion in a single day, and the phrase data privacy went from something only tech policy wonks worried about to something your neighbor was talking about at dinner. Here's what's really interesting about this moment, though. The Cambridge Analytica scandal wasn't really about one bad actor exploiting a loophole. It was about an entire business model. Facebook's core product was its ability to target advertising based on intimate knowledge of its users, their interests, their behaviors, their social connections, their psychological profiles. Cambridge Analytica had just done, in a crude and unauthorized way, what the platform's own advertising tools were designed to do in a more polished and sanctioned way. The scandal forced people to confront a question that had been lurking beneath the surface of the free internet for years. If you're not paying for the product, you are the product. Your attention, your data, your behavioral patterns, that's what's being sold. And this wasn't unique to Facebook. Google's entire business model was built on knowing what you were searching for, what you were interested in, where you were going, what you were buying. Amazon knew your purchasing history, your browsing habits, what you lingered on. These companies had built the most detailed profiles of human behavior ever assembled, and they'd done it with the willing participation of billions of people who clicked, "I agree," on terms of service that nobody actually read. Now, let me slow down here for a second, because this is one of those places where it's worth zooming out and thinking about the arc of the story we've been following. Remember way back at the beginning, when we talked about the internet's origins? The fundamental architecture that Vint Cerf and Bob Kahn designed with TCP/IP. It was decentralized by nature. No central authority. No single point of control. Packets finding their own way through the network. That was the whole idea. And for the first couple of decades, the internet mostly lived up to that vision. It was messy, it was chaotic, it was hard to navigate, but it was genuinely distributed. Nobody owned it. And then, layer by layer, centralization crept back in. First through the browser. Remember how Microsoft used its Windows monopoly to make Internet Explorer dominant? Then through search, Google became the de facto gateway to the web, and if your site didn't rank well on Google, it might as well not exist. Then through social platforms, Facebook became the place where people spent their time online, and publishers had to go where the people were. Then through mobile, Apple and Google controlled the two operating systems that ran essentially every smartphone on Earth, and their app stores became the gatekeepers for software distribution. Then through cloud infrastructure, Amazon Web Services, Microsoft Azure, and Google Cloud became the foundation that most of the internet services actually ran on. Each layer of centralization made things more convenient, more polished, more accessible. And each layer gave a small number of companies more power over the experience of being online. It's one of the great ironies of technology history. A network designed to survive nuclear war by having no center gradually developed centers more powerful than anything the original designers could have imagined. The regulatory response to all this was slow, uneven, and often confused. Governments around the world were trying to figure out how to govern entities that didn't fit neatly into existing legal frameworks. Were Facebook and YouTube publishers responsible for the content on their platforms? Or were they neutral conduits, like phone companies, not liable for what people said? In the United States, a piece of legislation called Section 230 of the Communications Decency Act, passed back in 1996 when the commercial internet was barely a toddler, had established that online platforms were generally not liable for content posted by their users. That legal shield had been essential to the growth of the internet. Without it, platforms would have been buried in lawsuits. But by the late 2000s, critics on both sides of the political spectrum were arguing that Section 230 gave platforms too much protection, too little accountability. Europe moved faster and more aggressively. The European Union passed the General Data Protection Regulation, GDPR, which went into effect in May 2018. It gave European citizens significant new rights over their personal data, including the right to know what data companies held about them, the right to have it deleted, and the right to opt out of certain kinds of data processing. Companies that violated GDPR could face fines of up to 4% of their global annual revenue, which for a company like Google meant potential penalties in the billions. GDPR was the most significant piece of internet regulation in the world at that point, and it forced companies everywhere to change how they handled data, because if you did business with European customers, you had to comply. But regulation was only part of the story. The deeper question was whether the internet's fundamental business model, free services funded by targeted advertising driven by data collection, was sustainable in a world that was waking up to its costs. And that question is still being answered. Meanwhile, the technology itself kept evolving, because it always does. Even as people debated the social consequences of platforms, engineers were building the next layers of infrastructure. And one of the most consequential developments of the late 2000s and early 2020s was the maturation of artificial intelligence, specifically machine learning and deep learning, as a practical tool integrated into almost every internet service. Now, AI research had been going on for decades, but what changed was the combination of massive datasets generated by billions of internet users, enormous computing power available through cloud infrastructure, and algorithmic breakthroughs in neural network architectures. Google had been using machine learning in its search algorithms since at least 2015, when it deployed a system called RankBrain. Facebook was using AI to identify faces in photos, moderate content, and target ads. Amazon was using it for product recommendations, warehouse logistics, and its voice assistant, Alexa. But the real watershed moment for public awareness came in late 2022, when OpenAI released ChatGPT, a large language model that could carry on remarkably fluent conversations, write essays, generate code, and perform tasks that felt, to many people, genuinely intelligent. And suddenly, the conversation about the internet shifted again. Because now the question wasn't just about who controlled the platforms or who owned the data. It was about what happens when artificial intelligence systems, trained on the vast corpus of human knowledge that the internet had accumulated over 3 decades, become capable enough to reshape how people work, learn, create, and communicate. The infrastructure that Licklider had dreamed about, that ARPANET had prototyped, that TCP/IP had standardized, that the World Wide Web had made accessible, that broadband had made fast, that smartphones had made portable, that cloud computing had made scalable. All of that infrastructure was now feeding something that felt qualitatively different from anything that had come before. And here's what's fascinating about this moment, if you think about it. The internet started as a way to connect computers so that researchers could share resources. Then it became a way to connect documents through hyperlinks. Then it became a way to connect people through social networks. And now it was becoming a way to connect human knowledge to machine intelligence in a feedback loop that nobody fully understood, not even the people building it. The engineers at companies like OpenAI, Google DeepMind, and Anthropic were remarkably candid about the fact that they didn't always know exactly why their models produced the outputs they did. The systems were too complex, too many parameters. GPT-4 was rumored to have over 1 trillion, for any human to fully comprehend what was happening inside them. And that uncertainty, that sense of building something powerful without fully understanding it, echoed something from much earlier in our story. Remember the early days of packet switching, when Paul Baran couldn't convince AT&T that his idea would work because it was so different from everything they knew? Or when Vint Cerf and Bob Kahn were designing TCP/IP and had to make choices about the protocol without knowing what kinds of applications would eventually run on it. There's always been this element of building into the unknown, of creating infrastructure whose ultimate uses couldn't be predicted by its creators. The internet has been, from the very beginning, an exercise in emergent complexity. Simple rules at the bottom producing unpredictable behavior at the top. And as the 2020s unfold, that complexity is deepening in ways that touch everything from geopolitics to the economy to the most intimate details of daily life. The internet is no longer something you go to. It's something you live inside. It's woven into the electrical grid, into medical devices, into cars, into home appliances, into the financial system, into military operations, into agriculture. The so-called Internet of Things, billions of sensors and devices connected to the network, means that the boundary between online and offline has essentially dissolved. Your thermostat is online. Your doorbell is online. In some cases, your refrigerator is online, though whether that's actually useful is a question reasonable people can disagree about. And all of this connectivity, all of this data, all of this computational power concentrated in a relatively small number of companies and countries raises questions about resilience and vulnerability that would have been very familiar to the people who started this whole thing. Because remember, the original motivation for packet switching, the reason ARPA funded the research in the first place, was survivability. The network was supposed to keep working even if parts of it were destroyed. And the modern internet, for all its miraculous capability, has developed some troubling single points of failure. When Amazon Web Services had a major outage in December 2021, it took down a significant chunk of the internet with it. Streaming services, smart home devices, even some robot vacuum cleaners stopped working. That's a long way from a decentralized network with no critical nodes. So here we are, in a world where the internet has become the most important infrastructure humanity has ever built, more essential than roads, more pervasive than electricity, more transformative than the printing press. And the story of how we got here, from Licklider's memo in 1963 to the world we live in now, is really a story about people reaching for something they couldn't quite see yet, and then building it anyway. That's really what it comes down to, isn't it? Not a single invention, not one genius in a lab, but this long, messy, deeply human process of imagining a thing that doesn't exist, and then, piece by piece, argument by argument, failure by failure, willing it into being. Licklider imagined a network of minds before the technology existed to connect them. Baran imagined a communication system that could survive a nuclear war, and people literally laughed at him. Cerf and Khan imagined a universal protocol that could stitch together incompatible networks, and they wrote it on the back of an envelope in a hotel lobby. Berners-Lee imagined a web of linked information and built it essentially by himself on a Next computer at CERN, and for a while, almost nobody cared. None of these people could see where it was all going. None of them predicted social media, or streaming video, or cloud computing, or smartphones, or any of the things that define the internet as we experience it today. They were solving the problems right in front of them, and the cumulative result was something none of them could have anticipated. And that, honestly, is one of the most comforting things about this whole story, if you think about it. Because right now, in this moment, the internet feels like it's at another one of those inflection points, one of those moments where the ground is shifting and nobody's quite sure what comes next, and the uncertainty can feel unsettling. But the history tells you that this is actually normal. This is how it's always been. The internet has never been a finished thing. It's always been becoming something else. So let's talk about where we are right now and where things seem to be heading. Because even though nobody can predict the future with any certainty, you can see the trajectories. You can see the forces in motion. One of the biggest forces, and we touched on this, is artificial intelligence. But it's worth sitting with for a moment longer, because the relationship between AI and the internet is more intimate than most people realize. The internet didn't just enable AI, it fed it. Every search query you've ever typed, every photo you've ever uploaded, every comment you've ever posted, every product review, every email, every video, all of that became training data. The large language models that exploded into public consciousness with ChatGPT in late 2022, those models learned from the internet. They ingested billions of web pages, books, articles, forum posts, code repositories. In a very real sense, these AI systems are a distillation of collective human expression as captured by the internet over the past 3 decades. The internet gave AI its education, and now AI is beginning to reshape the internet in return. Think about what that means for search, for instance. For 25 years, the basic interaction model has been the same. You type keywords into a box, you get a list of links, you click through to websites. That model made Google one of the most valuable companies on earth. But if you can just ask an AI a question and get a synthesized answer directly, why would you click through 10 blue links? Google knows this is an existential question for them, which is why they've been racing to integrate AI into search. But the implications ripple outward. If fewer people click through to websites, what happens to the publishers, the bloggers, the journalists, the small businesses that depend on search traffic? What happens to the advertising model that funds most of the free internet? These aren't hypothetical questions anymore. They're playing out right now, in real time, and nobody has definitive answers. And here's what's really interesting. This is actually a pattern we've seen before in this story. Remember when the World Wide Web came along and disrupted the existing internet services? Gopher, Wayaz, all those earlier systems that were working just fine until something better showed up? Or when broadband disrupted dial-up, and the whole ecosystem of content that had been designed for slow connections suddenly had to adapt. Or when mobile disrupted desktop, and every website had to be redesigned for a 4-inch screen. The internet has gone through these platform shifts before, and each time, the transition was messy and painful and created winners and losers. But the overall trajectory, was towards something more capable and more accessible. That doesn't mean we shouldn't be thoughtful about the transition. It just means that disruption is baked into the DNA of this technology. It's what the internet does. It disrupts, including itself. Another force that's shaping where things go next is the question of governance. For most of its history, the internet operated in a kind of regulatory vacuum. Governments didn't really understand it, and by the time they started to, the major platforms were already enormous and deeply entrenched. But that's changing. The European Union has been the most aggressive, not just with GDPR, but with the Digital Services Act and the Digital Markets Act, both of which came into force in 2022 and 2023. These are sweeping pieces of legislation that impose real obligations on large platforms, requirements around content moderation transparency, restrictions on how personal data can be used for targeted advertising, rules about interoperability. The idea is to crack open some of that concentrated power we talked about, to make it possible for smaller competitors to exist. Other countries are taking different approaches. India has implemented data localization requirements. Brazil has its own internet civil rights framework. China, of course, has built what's sometimes called the Great Firewall, a comprehensive system of censorship and surveillance that creates what is essentially a separate internet with its own search engines, social platforms, and messaging apps. The notion that the internet would be a single, unified, borderless network, that dream from the early days, has fractured along geopolitical lines. The term people use is the splinternet, and while it's a bit of an exaggeration, the trend is real. Different countries are making different choices about what the internet should be, and those choices are creating different experiences for different populations. And this connects back to something fundamental about the internet's design. TCP/IP doesn't care about national borders. A packet is a packet. The protocol doesn't know or care whether the data it's carrying is a love letter or state secrets or a cat video. That neutrality, that beautiful indifference to content, was a design choice. And it was a choice that reflected a particular set of values, a particular moment in history, a particular group of people who believed that open communication was inherently good. And maybe they were right. But the world has gotten complicated, and the consequences of open communication at global scale have turned out to be more ambiguous than the early pioneers imagined. Let's come back to something quieter for a moment, though, because amid all the big forces, AI, regulation, geopolitics, there's something easy to lose sight of, and it's maybe the most important thing of all. The internet, at its core, is still about people connecting with other people. That's what Licklider was really dreaming about. Not machines talking to machines, but people thinking together, collaborating, sharing knowledge across distances that would have been insurmountable in any previous era of human history. And that still happens. Every day, it still happens. A teenager in rural Montana takes a free course from MIT and discovers they have a gift for mathematics. A doctor in Lagos consults with a specialist in London about a difficult case in real time over a video call. A grandmother in Seoul video chats with her grandchildren in Toronto and watches them blow out birthday candles from 8,000 kilometers away. An open-source developer in São Paulo writes a piece of code that gets incorporated into software used by millions of people they'll never meet. A person going through something painful and isolating types their experience into a forum at 2 a.m. and discovers they're not alone, that someone on the other side of the world understands exactly what they're feeling. These aren't dramatic stories. They don't make headlines, but they're the real internet, the one that exists underneath the platform wars and the algorithm controversies and the regulatory battles. And they're worth remembering, especially when the discourse about the internet gets dark, when it feels like the whole thing has gone wrong, like the technology has betrayed its promise. Because the promise is still there. It's just gotten buried under layers of commerce and politics and scale. There's a concept in engineering called graceful degradation. It means designing a system so that when something fails, the system doesn't collapse entirely. It falls back to a reduced but still functional state. The internet was designed with this principle in mind, at least at the protocol level. And in a broader, more metaphorical sense, I think the internet has demonstrated a kind of graceful degradation of idealism. The utopian vision of the early days, that the internet would democratize everything, that information wants to be free, that connecting everyone would automatically make the world better, that vision has degraded. It was too simple. It didn't account for human nature in all its complexity. But what's left, what the system has fallen back to, is still remarkable, still functional, still, on balance, one of the most extraordinary things our species has ever created, and the people working on it haven't stopped. Right now, engineers are working on new protocols to make the internet more private and more secure. There's a push toward encrypted DNS, toward end-to-end encryption as a default, toward decentralized identity systems that could give people more control over their own data. There are projects exploring decentralized social media, where no single company controls the platform. Whether these efforts will succeed at scale is an open question, but the impulse is the same one that drove the original designers, the belief that the architecture matters, that how you build the system shapes what the system becomes. You know, Paul Baran, the guy who came up with distributed networks and packet switching back in the early 60s, the one whose ideas were too radical for AT&T. He gave an interview late in his life where he said something that stuck with me. He said that the internet was really the work of 1,000 people, most of whom would never be recognized. And he was right. For every Licklider and Cerf and Berners-Lee, there were hundreds of engineers and researchers and system administrators and standards committee members who did the unglamorous work of making things actually function. People who debugged routing tables at 3 a.m. People who wrote documentation that nobody would ever read, but that kept the whole system coherent. People who laid fiber optic cable under oceans, literally threading glass through the deep sea so that light could carry your voice to the other side of the world. That's the real story, when you get down to it. Not any single invention, not any single person, but this vast, ongoing, collective act of building, layer upon layer upon layer, copper wire, then fiber optics, then radio waves, analog signals, then digital packets, room-sized computers, then desktops, then laptops, then phones that fit in your palm and contain more computing power than everything NASA had when they put people on the moon. Each layer built on the one before it, each generation of engineers standing on the shoulders of the last, solving problems that the previous generation couldn't have imagined and creating problems that the next generation will have to figure out. And that's still happening. Right now, tonight, while you're lying here listening to this, someone somewhere is writing code that will change how the internet works. Someone is testing a new protocol. Someone is arguing in a standards meeting about the right way to handle some obscure edge case that will affect billions of people who will never know the argument happened. The internet is still being built. It's never been finished. It probably never will be. So let that thought settle in as you drift off. This thing that surrounds you, this invisible infrastructure that carries your words and your memories and your connections to the people you love, It started as an idea in the mind of a quiet psychologist who believed that computers could help people think better. And then, one person at a time, one problem at a time, one late night at a time, it became the world we live in. It's imperfect. It's messy. It's full of contradictions. Decentralized in design, but increasingly centralized in practice. Built for resilience, but riddled with fragilities. Created to connect people, but sometimes making them feel more alone. It's a mirror of us, really. Of all our brilliance and all our blind spots. And it's still becoming something new. Every single day, it's still becoming something new. And that, more than anything, is what makes it such a remarkable story. It doesn't have an ending. It just keeps going, like a signal traveling through fiber at the speed of light, racing toward whatever comes next, carrying everything we are with it into the dark, into the distance, into tomorrow.